So, and we're only doing sections 1 and 2 over here in chapter 10. So, if you look through couple different examples, like here, they're talking about, I think between two friends, like flipping a coin and seeing if your friend is cheating. So you can kind of take their results and use that to create a null hypothesis and an alternative hypothesis. So the idea here is, again, you are basically talking about, is certain thing happening or not happening, just in more generic terms. So we're talking about, hypothesis testing is a procedure based on sample evidence and probability, and you're using those to, use to test statements regarding a characteristic of one population or not. And, that's kind of what we are defining our hypotheses as, basically being a characteristic for one or more population. So, this one here, when we talk about null hypotheses, that's basically the characteristic that you are testing. So, we're basically saying the null hypothesis is a statement with no change, no effect, or no difference, and is assumed to be true till you have, evidence proving it to be false, or basically being otherwise. The alternative hypothesis would, of course, be a statement where you're trying to find the evidence to support, that basically your null hypothesis is not true. So we use H sub 0 and H sub 1. So H sub 0 is for the null hypothesis. H sub 1, of course, is for your alternative hypotheses. And it will actually depend on what kind of test you are doing. So, if you have a hypothesis where we say, okay, your parameter could be, depending on what you are using as your characteristic, it can be equal to a value or not equal to a value. So when it's equal and not equal, that's when we call it a two-tailed test. If you say, the null hypothesis, whatever value you are looking at, but if you feel like something is actually less than that value, that's when you're looking at a left-tailed test, right? Because you're saying less than, which means you are going to be, lesser than on the left-hand side. If it is greater than, then that's when we say this is a right-tailed, test. So it kind of depends on, what your null statement is and what your alternative is. And based on that, you get into what kind of, two-tail, left-tail, right-tail you will have. So I would definitely ask you guys again to kind of read a little bit on that, just to get a bit more familiar and, get some technical information out of that. And then we actually talk about type 1 and type 2 errors. And basically, when you think about type 1, type 2 errors, if my pen will cooperate, we're talking about if you reject the null hypotheses, when the null hypothesis is true, of course, that means we made a wrong decision, and that's what we call as type 1 error. So you can say, and I kind of like this table, and you'll see this commonly used in most statistics textbooks. So the idea is your null hypothesis was true, but you still rejected it. So that's your type 1 error. Now, if you did not reject your null hypothesis when actually your alternative hypothesis was true, but you kept the null hypothesis, you did not reject it, again, obviously that's a wrong decision. So that's a type 2 error. So type 2 error, as you can see, is the alternative was true, but you still did not reject the null hypothesis. So that's where we're making the type 2 error. And then you can see in the other cases, we are talking about if your null hypothesis is true and you did not reject it, obviously that's the right decision to make. So we are good to go on that. If your alternative hypothesis was true, which means you should have rejected the null hypothesis, the original statement that we had, you rejected it, then of course that was also a good decision to make. So it really depends on, and this is going to be very individualized based on each problem you look at, each example you look at. But this is kind of the general premise, when you're working with hypotheses testing. So you've got null hypotheses, alternative hypotheses, And then the decisions you make based on that will lead you to either correct conclusions or type 1 or type 2 errors. So you can see again, they've got a whole bunch of examples in there. You know, of course, we again talk about level of significance, kind of like we did with the confidence levels in the previous chapters, but here we're talking about level of significance. And the one thing to keep in mind when you're working with level of significance is if you increase your level of significance, it will make it more likely that you will reject your null hypothesis. So in this case, we actually try to keep the level of significance pretty small. You want to keep it small. So you will see again in this examples, they're talking about if consequences are severe, the null, oh, where did you go? If the consequences are severe, the level of significance should be small. So that's an alpha value of 0.01. And they're saying, you know, if the consequences are not severe, then, you know, we can think about a higher level of significance, so 0.05 or even 0.10. So it will really, again, kind of depend on what type of examples you're looking at. And again, you can kind of read a little bit more detail on that. So let's pick an example over here from our 10.1 section, just to kind of, you know, give us a little bit of an idea of which type of alternative hypothesis statements we need to make, and, you know, just the different types of errors and stuff we can kind of encounter. So the first example I actually had for us to look at is number 9. And I'll try to make this a little bit bigger so you can read it better. You've got a couple different examples on this one, so, you know, hopefully this one will give you an idea of how to do the rest of them. So as you can see here, we're saying the standard deviation in the pressure required to open a certain valve is known to be, and you can see that's your standard deviation symbol, sigma, is 0.6 psi, parts per square inch. And then they're telling you, due to changes in the manufacturing process, the quality control manager feels that the pressure variability has been reduced. So you can see, I'm going to try and make this guy smaller here. Whoa. Okay, not sure what happened. Okay, sorry, I keep clicking on things that I'm not supposed to click on. Okay, so let's get back in here. So they're telling us the standard deviation is required or is known to be 0.6 psi, but then they're telling us because of the changes, the quality control manager feels that the pressure variability has been reduced. So in this case, when you're actually working through your hypothesis testing over here, I'm going to write this out and then, you know, we can put it in there. So you are talking about standard deviation. So that's going to be our variable. And we're saying it is known to be 0.6. So that's what your first characteristic is, that our standard deviation should be right at 0.6. So this is your null hypothesis. So, you know, again, nothing fancy. It's just whatever that parameter or characteristic you are using. But then the manager has a feeling that it's actually been reduced. So that's your null hypothesis. So you're talking about reducing, or he feels that it has reduced, he or she. So this is where you will actually say it's reduced, which means it's less than. Come on, pen. And it would be 0.6. If they had said increased over here, if this had been increased, then you would be using the greater than symbol. So it's really just as simple as what the observation they are making over here. So since this was reduced, that's the reason why we are using the less than symbol. So coming back over here, they've broken it down into like 6 parts to this question. So standard deviation symbol equal to 0.6. And then the alternative is he feels or she feels that the pressure variability has been reduced to less than. 0.6. Okay, so that's there. Now they're actually getting into defining what would cause us to have a type 1 error and what would cause us to have a type 2 error. So remember type 1 error, and let's see if it will let us go back to our textbook page. There we go. So let's find that table one more time. So remember, type 1 error happens when the null hypothesis was true, but we rejected the null hypothesis. So that's basically where you need to think about where the type 1 error is happening. So that means for our example, if you look at the different statements over here, the manager rejects the null hypothesis when it is true pressure variability. The second one says the manager rejects the hypothesis that the pressure variability is 0.6 when the true pressure is less than 0.6. So remember, type 1 error is null hypothesis is true and you end up rejecting it. So if you look at that first statement, it says the manager rejects the hypothesis that the pressure is 0.6 when it is the true pressure variability. So there's no question of less than, because in your null hypothesis, we have set it to equal to and not less than. So in this case, you are rejecting the null hypothesis, which means you're not going with fails to reject. So it's got to be between one of the two rejects, and then you kind of have to see how they have worded the statement. So in this case, it should be it is true pressure variability. So that's actually going to be option A over here. And then they're going to say, okay, so which of the following would be a type 2 kind of error? So remember, type 2 error happens when the alternative was true, but we still did not reject the null hypothesis. So you're basically saying, the alternative would have been true, but you're basically saying the null hypothesis is true. So this is where, we're making a type 2 error then in our decision. So keeping that in mind, this is where the idea is we fail to reject the null hypothesis. So when we're talking about fail to reject, then these would be the two options you are looking at. And then you kind of have to see again how the true other statements, the remaining half of the statement is worded. So type 2 error is when the alternative hypothesis is true, but we do not reject the null hypothesis. So part A says the manager fails to reject the hypothesis that the pressure variability is 0.6 when the true pressure variability is less than 0.6. And part C says the manager fails to reject the hypothesis that the pressure variability is 0.6 when it is the true pressure variability. So our null hypothesis, of course, alternative was that the manager felt the pressure variability was reduced. So since we know the alternative has to be true, which option would you be leaning towards, A or C? Because we know the alternative hypothesis is true, but we fail to reject the one. So we're saying basically pressure variability is 0.6 when in fact the alternative was true, which means the pressure has dropped. Dennis, Jeffrey, yeah, very nice, guys. So yeah, the idea here is, Naomi, very good, that actually the pressure variability has dropped, but you are still not rejecting that it is still at 0.6. Because, otherwise this statement here is very similar to what we picked in the type 1 error. So that's the same sentence formation you have over here. And, obviously, if that was the true pressure variability, then we wouldn't reject the null hypothesis, which means we would have had a correct conclusion. So they're asking you for type 2 error where alternative is true, but we still do not reject the null hypothesis. So yeah, very nice, guys. It is going to be, sorry, option A in this case. So it's really just, comes down to the wording. And that's the reason why I picked this example, because you do have a few examples with this one where they will ask you, identifying how will you make the type 1 error, type 2 error, and then, different examples will have you construct different types of your null and alternative hypotheses. So this is one example, and then let's take a look at another one here. And this is number 17. So this one is talking about a can of soda is labeled as containing 16 fluid ounces. So, that's your capacity. The quality control manager wants to verify that the filling machine is not over filling the cans. And then they're asking us to complete parts A through D. So not overfilling the cans. So can you tell me, what do you think your null and alternative hypotheses will be? Now, just to kind of give you an idea, when you look at the variables here, they're giving you P, which stands for probability. Of course, sigma stands for standard deviation, and mu, as we know, stands for mean. So here they're talking about a soda can is being labeled 16 fluid ounces, and the manager wants to make sure that we're not overfilling the can. So in this case, you are kind of talking, of course, staying with that average. So we want to keep the average of these cans at, this given value of 16 fluid ounces. So can you start me out with, and you don't have to use the mu variable, just give me what your null hypothesis should be. So should it be equal to, greater than, less than, just based on this example here? And it's okay if, you're unsure at the beginning, because that's kind of where we are right now. Yeah, it should be equal to, right? Because we want that null hypothesis to be equal to whatever the value is going to be. All right, nice job, guys. So this should be equal to 16. Now, the quality control manager is talking about not overfilling this, not overfilling the can. So what do you think that should be? Less than, greater than? If it's not equal to, you can just type in not, the word not with the equal to symbol. Okay, Dennis, you're going with greater than. What about the rest of you? Okay, let's see. Jeffrey, you went with less than. Darla, less than. Naomi, less than. John, less than. Wow, most of you went with less than over here. All righty. So you are saying the can should be less than 16 ounces? And Dennis, you are saying the can should be greater than 16 ounces, right? Because that's what you are going with. Yeah, so since they're talking about not overfilling, I'm kind of thinking not overfilling, which means we don't want it to be greater than 16. But let's put it to the test, because I'm with Dennis on this one, but we could be wrong. So obviously the first one is going to be equal to, and that is 16 fluid ounces. And you know what, since the majority of you said 16, I'm going to try that out first. Sorry, less than 16. So we don't want the cans overfilling. Yeah, see, and that's where I was unsure about. So let's try with greater than. Now, as you can see, everything else it accepted, but that one box. So if it actually said underfilling, guys, that's when you would have used the less than symbol. So since they're specifically talking about, overfilling, filling. So since this was overfilling, we're going with greater than. If it was under filling, you will go with less than. And I have actually seen one example, because when I was kind of flipping through these examples, they can actually also say it should not underfill nor overfill. So if they give you both options, not under and not over, that's when it's actually going to be not equal to. So this question does actually go back and forth between different options. So just kind of keep that in mind. So if they say not under nor over, that's when you're using not equal to. So just to be a little careful about with these examples here. All righty, so let's clear this out. Then they are saying part B, the quality control manager obtains a sample of 76 cans and measures the contents. The sample evidence leads him or her, I guess, to reject the null hypothesis. So he's obtaining a sample of 76 cans. He measured the contents. So of course he's trying to see, if everything is at 16 ounces or not. And they're telling us he is rejecting the null hypothesis. So write a conclusion for this hypothesis test. So what is making him reject the null hypothesis? What would you say? Because they're giving you there, and your options here are.
He's finding more than 16 ounces in a can.
Yeah, because that's kind of what he was. Stop doing that. Okay, so this is your two options, is not or is. So they're asking you, there is not sufficient evidence or there is sufficient evidence to conclude that the machine is out of calibration. So we know he's getting a sample of 76 cans, right? So based on that, would you say there is enough evidence or there is not enough evidence? Because 76 cans isn't that a decent amount of number? Because 76 cans, and of course they don't give us all the breakdown of what the measurement for each was, but I would say yes, if he took the sample of 76 cans and he is rejecting the null hypothesis, that means he has enough evidence. So I would definitely say is, and obviously that is the way to go. Okay, so now we have taken care of that part. Now we're getting into, suppose in fact the machine is not out of calibration. So he has rejected the null hypothesis, which led us to believe, okay, so there's enough evidence to reject the null hypothesis, which means the machine is out of calibration. But now they're saying, okay, what if the machine is actually not out of calibration? What kind of error have you made? So if the machine is not out of calibration, but we still rejected the null hypothesis, so what kind of error are we looking at? And let's go back over here. So type 1 or type 2 error? Okay, Dennis, you've got 1, Jeffrey 1, John 1, Darla 1. Yeah, because we are saying that you rejected the null hypothesis, whereas that was not true. Your machine was not out of calibration, which means, yeah, very nice, guys. We have made a type 1 error. So that is type 1 error has been made since the sample evidence led the control manager to reject, and they're telling us he rejected right over here, when the null hypothesis is true. So you can see they're just kind of breaking that statement up into 3 parts. And then the last one is actually getting into the management has informed the quality control department that it does not want to shut down the filling machine unless the evidence is overwhelming that the machine is out of calibrations, which means they would actually have to go with a much larger, I would imagine, sample size, if they wanted to get really overwhelming evidence. Now, what level of significance would you recommend the quality control manager use? And your level of significance, as you can see, is going between these 3 numbers because this is the probability of a type 1 error. So, depending on which level of significance you use, that will tell us what kind of probability will we have for the type 1 error. So this is where I was kind of mentioning to you guys earlier, if you increase the level of significance, it's more likely that your null hypotheses will be rejected. So, they were talking about consequences. Are the consequences, big enough that we need to keep a low level of significance, or are the consequences not that worrisome that you can go with a higher level of significance? So if you had to try out, which number would you go with? 0.01, 0.1, or 0.05? Yeah, Dennis, Darla, Jeffrey, John, I like that idea because, you want to keep your level of significance low because, in any given situation, we really wouldn't want to reject the null hypotheses unless, like they're saying, there's got to be overwhelming evidence. If you want to keep the probability of your type 1 error small, you want to keep the level of significance small also. So does that kind of make sense with the level of significance? So these are actually the type of questions you have in section 10.1. So there's actually not a whole lot of calculation that I found because they're kind of, I think, setting the stage is what I think about as section 10.1. And then in 10.2 is where we're going to get into more calculation-based examples. So this one over here, again, you've got a couple different examples which kind of follow this same path. So I would definitely ask you guys to look through that and see how you feel. But let's get into a calculation problem here because I'd at least like to do one, maybe two calculation problems. We'll see how long it takes us. So this one over here is 10.2, and let's take a look at, and again, I was trying to find one that kind of had multiple parts to it so we could walk through the different parts. And I'll make this a little bit bigger so we can read the problem, and then I'll collapse it back down. So they're saying 20 years ago, 52% of parents of children in high school felt that it was a serious problem that high school students were not being taught enough math and science. So this was 22 years ago, 52% of the parents felt that their kids were, not being taught enough math and science in high school. A recent survey, excuse me, a recent survey found that 266 out of 800 parents of, these kids in high school felt that it was a serious problem, they were not being taught enough math and science. So, this is recent. So, obviously 20 years moving forward. So they want to know, do the parents feel differently today than they did 20 years ago? So you're basically comparing the results from today, which is the 266 out of 800 parents compared to the 52% of parents back then. And this one, they're asking us to use our level of significance as alpha equals 0.1. So in this case, you will see again, they're asking us to start out with using, you're actually just checking to see if we are meeting the requirements for hypotheses testing. So again, you will see they're having us do n times p sub 0, which is your initial probability, minus the p, 1 minus p sub 0. So this number has to be larger than 10 to meet the requirements. Your sample size has to be less than 5% of the population. And, of course, you have to have a random sample. So two of the things we are actually going to make an assumption for, because if you go back and read the language, they didn't actually tell us this was a random sample. Nowhere in the problem, and I've made it small, so if you can read it, you can try to read it. They don't really mention it's a random sample. But I would say if, and that's kind of a dangerous thing to do, but because we know this is a textbook example, it's going to work. In practicality, you would really want to make sure that this was a random example or random sampling. But here we are actually going to make an assumption and say, yes, this is a random sample. So you will actually pick this option that says can be reasonably assumed to be random, because they're not giving us that this is random, or for that matter, they're not saying this is not random sampling. So that's why we're making an assumption that this is random sampling. I mean, if you think about it, we're talking about 800 parents of high school students. And if you think about the population, 800 has to be less than 5% of the population, because, if 800 is more than 5%, that means your population size is not that small. So we can say, yeah, again, reasonably, we can assume that the sample size is, less than 5% of the population size. Now, this one here, they do want you to calculate. So in this case, your N value is actually coming from the 800 parents. So that's our N value. The P sub 0 is actually this percentage over here. So that's our P sub 0. So N is 800, parents. And then your P sub 0 is given to us as 52%. So again, convert that to a decimal, will be 0.52. So when they asked us to do this little math over here, N times P sub 0 times 1 minus P sub 0, you are doing 800 times 0.52 times 1 minus 0.52. And sorry, I do apologize. I didn't get a chance to create our Google Sheets like I normally like to use for this one. So I am actually going to, I guess, wing it. And I'll, make it a little bit more formal next time. Actually, let me see if it will. Let me go from here somewhere. It keeps changing my drive on me, sorry. So we'll just create a blank one for now. And so this is going to be N times P sub 0. And again, like I said, I'll have to fix that later on. 1 minus P sub 0. So again, your N value is 800. P sub 0 is 0.52. So again, if we just use the built-in functions, I can take my 800, multiply that with the P of 0.52, and then multiply that with, and in parentheses, I would put the 1 minus 0.52. And you can see that number, obviously, because you're multiplying 800 with, basically half and half, it just breaks it down to almost 200. So you're getting 199.68. And we just needed this to be, well, larger than 10. So let's see, they want us to do one decimal place. So 199.68, so that would be 0.7. So you can see 199.7, which is definitely greater than 10. So the calculation works out, it's greater than 10. We are saying, we can reasonably assume that you have a pretty large population of parents who have kids in high school. So 800 is going to be less than 5% of our population size. And again, like I said, we can reasonably assume that our sample is random. So making those assumptions and then looking at our calculation here, we can say the requirements for testing the hypotheses are satisfied. And let me clear out all of this. And so we can go ahead and check our answer. And there are certain assumptions that you do make as a statistician, because you can look at previous records and something like that, because you're not always going to be able to find all the information you need. So these are reasonable assumptions to make. Okay, so we've got our requirements met for hypothesis testing, which means now we need to talk about our actual test. So here, guys, we're actually testing the probability of the parents, because again, we're talking about 52% of the parents 20 years ago 26 out of 800 parents now, and we want to know if they're feeling differently. So you are actually testing the probability of these, percentage of parents who feel that their kids are not being taught, enough math and science. So your null hypothesis is actually going to be based on the original percentage value, which is that 52%. So this will be 52%. And then they're just saying, do the parents feel differently today than they did 20 years ago? So in this case, there's no less than or greater than. We're actually saying the alternative hypothesis has your probability changed from 52%. So as you can see, this one here, they were not talking about has the percentage decreased or has the percentage increased. They just said, do they feel differently? And that's the reason why we're going with the not equal to. So those are going to be our null and alternative hypotheses. So again, probability is equal to 0.52. So just going with that original value. And then this one will be probability is not equal to 0.52. Okay. Now this z sub 0, I will need to show you that. Let's clear this out. And you will actually need to go into 10.2 for that. Okay, so this is actually where we're getting into, okay, not here. So you can see again, we've got our little population proportion over here. The p hat is x over n. We will need this calculation over here to get into our, z sub 0 calculation. We will need to calculate our little standard deviation value that you're seeing over here, the square root of p times 1 minus p over square root n. So all of these actually put together can give us that test statistics of z sub 0. And you can again see there's quite a bit of information here for you to read through, but this is actually where we are right now. We've got our population proportion, and since we set up our hypothesis testing as p equals the number and p not equals, you will see we are actually looking at this two-tailed hypotheses testing over here. And then in this case, we have our little formula for calculating our test statistics. And you can see with the classical approach and p-value approach, we are looking at the same test statistic calculation over here, and then we get into our right tail, left tail, two-tailed discussions over here. So that's kind of what we're looking at, but this is the formula that we are using for our test statistic that we need to work on next. So we need to calculate that p hat first, which is our population proportion. So I'm actually going to come back to our and right now I'm just going to type in as p hat. So remember, your p hat is your x divided by n, which for us, the x value was the 266 out of 800. So that's exactly what you are doing. Stop moving. 266 out of 800. And you can leave it at this. I was looking through your notes and I think they say round it to 3 decimal places. So if you have a really long value that comes up here in your examples, you can round it to 3 decimal places. They don't really tell us that specifically in here, but if you look through, the examples, you will see that most of the time they will round it to 3 decimal places. So you can see that right here, 0.438. So if you want, we can go ahead and round this guy to 3 decimal places. Okay, so that's our p hat value. Let me see if I can actually copy this over so we don't have to keep going back and forth between our formula. Okay, there we go. So that'll make it easier for us to, look through. Okay, let's put him back here. Alrighty, so now you've got your p hat. Our p sub 0 is going to be this number over here. So that's p sub 0. And then, of course, this was our n value. So just kind of using all of those on the numerator. And I'm going to put that in parentheses. We're going to do p hat, which is the 0.333, minus the p sub 0, which is 0.52. So as you can see, you are subtracting a smaller minus a larger number. So you are actually going to get a negative value in there. And you can see just that calculation is giving us negative 0.188. So yeah, that will happen. You will get a negative value in here. Now for the denominator, we're putting all of that in the square root. So again, with Google, you have to use capital letters for your function. So that's square root of p sub 0, which is again the 0.52 times, and then in parentheses, I'm going to do 1 minus the 0.52 again. So again, guys, this is making our numerator, right? The p times 1 minus p on the top. And then you're dividing that by the n value, which is 800. And closing this parentheses closes the parentheses for the square root. So, again, I'm just typing this all into one cell, but if you wanted to, you can obviously do it in couple steps, break it down into steps if you wanted to. But this is actually our Z statistics, and this is what we will need to compare when you are doing these hypotheses testing. So find your test statistic, and then based on our testing, are you doing two-tailed, left-tailed, right-tailed? Depending on that, you have to calculate your critical value. So you will see when we are doing our two-tailed, you're actually looking for a critical value of plus or minus Z sub alpha divided by 2. Now the alpha value is given to us in the problem itself. So this will be alpha divided by 2. And then look at the step 4 over here. Based on what your critical value comes out to be, if your test statistic, the number that we just calculated, the negative 10.6, looking at that, and then the Z values we get over here, if your test statistic is going to be less than the negative critical score over here, or if your test statistic is going to be greater than the positive critical value, then in that case, you reject the null hypotheses. And so to do that calculation, we're actually going to come back here. You can see our alpha value is given to us as 0.1 as our level of significance. So if you actually go, oh, you know what, let's go ahead and put this number in. We had negative 10 point, and they want 2 decimal places. So that will be, putting this down to 2 decimal places is going to be 0.62. So let's do the test statistic part. And then this is where we actually need to enter our test statistics. So if you had a red-tailed or right-tailed test, guys, you would pick option A with the Z sub alpha. Since we have a two-tailed hypothesis testing, you are actually going with option B with the plus or minus Z alpha sub 2. And this is where you want to click on this little standard normal distribution table and scroll all the way down. And you will see the critical values for our hypotheses testing over here. So our level of significance was 0.1. So right here, you can see 0.1, and that is going to be this level of significance, 0.1. And I'm going to make this larger, but I just kind of wanted to show you where our numbers are coming from. So our level of significance is 0.1. This is a two-tailed test. So our critical value is actually going to be or 1.645 plus or minus. So you can see based on the different level of significance, which test you are doing, you've got your different critical values over here. So all of this is right here. When you click on this page 2 and scroll down to the bottom is where you will find it. So 1.645 is what we're basically looking at. And they want us to only do this to 2 decimal places. So we had plus or minus 1.645, rounding it to 2 decimal places. Well, technically that should be 1.65. So let's check that. Actually, I believe even if you typed in 1.64, it might accept that answer also, but obviously with rounding rules, this guy goes up to 6.5. Okay, so you've got your general hypotheses set up with the null hypotheses, alternative hypotheses. Based on that, we calculated our test statistic. So, with the information given to us is how we came up with that test statistic. Now, this is actually where the comparison happens. So remember in your handout, they're telling you if z sub 0 is less than the negative z of alpha divided by 2, or if it's greater than. So let me write that down over here. So if your test statistic z sub 0 is less than, negative z alpha sub 2, or if z sub 0 is greater than the positive z alpha sub 2, then this is when you are rejecting the null hypothesis. And right. So let's do our comparison over here. Our z sub 0 is negative 10.62. Our z sub alpha, and if you use the negative one, I'm kind of looking at this first part here, is negative 1.65. What symbol would you use here? Is it less than or not less than, greater than? Which symbol would we put between basically negative 10 and negative 1.65? Yeah, negative 10.62 is less than negative 1.65, which means we reject the null hypotheses because this condition is being met, obviously looking at those 2 numbers. So now you are choosing between, okay, if I'm rejecting the null hypotheses, then I am looking at these 2 options over here. You've got, there is insufficient evidence to conclude that the number of parents who feel that the students are not being taught enough math and science is significantly different from 20 years ago, or there is sufficient evidence that the number of parents who feel that students are not being taught math and science is different. So if you go back and look at your p hat, which was the value based on parents from today, the 266 out of 800, that is a 0.333. From 20 years ago, they had a 0.52, right? So that's 52% compared to 33.3%. So which option would you pick? Is there sufficient evidence, or is there no sufficient evidence or insufficient evidence? Darla, you're going with option C. Dennis, you're going with C. So you guys are saying there is sufficient evidence. Yeah, because you've got the 2 results to look at. We went through the whole process of calculating our test statistic, looking at, comparison between the critical values based on our level of significance. And yeah, we can say, yes, we have sufficient evidence to make this conclusion. So, like I said, it really is a very different kind of math that you are looking at, from what we've done, because the idea is you've got your mean, your standard deviation, all of that, we got into probability distributions and stuff. But now we're really trying to see, how the studies are changing over time, or, how different variables can happen. We saw in the last example in terms of pressure variability. Here, we're just saying in 20 years, has the feeling of people changed? So any questions as we walk through the steps of this example over here? Any part that you needed extra help with or did not make sense? Okay. Let's see if we can find another example here. Yeah, I had seen this one, but I'll be honest, I have not had a chance to work through this, but we can kind of work through this together and see what we come up with. So this is question number 11. And let's take a look at this one here. So this one is talking about two professors at a local college developed, just one second, guys. Two professors at a local college developed a new teaching curriculum designed to increase students' grades in math classes. In a typical developmental course, 57% of the students complete the course, with the grade, letter grade of A, B, or C. In the experimental course, 18 students enrolled, 14 completed the letter grade with A, B, or C. So is the experimental course effective at a level of significance of 0.025? So, again, they're kind of saying, from the typical developmental course to the experimental course, how are the, performance of students changing? So with this one over here, what do you think our hypotheses should look like? And again, your variables are sigma, mu, and p. So should we go with sigma, p, mu as our variable when we're setting out this hypothesis? And again, they're saying, in a typical development course, Jeffrey, you're going with P. 57% of the students complete the course, and then 14 out of the 18 in the experimental. Yeah, because they're giving you a probability here, right? There's no standard deviation. And unlike the pressure variability, or sorry, not pressure variability, the soda can example, they gave us the fluid ounces. So we knew the average had to be those fluid ounces. So in this case, you are talking about P as our variable. And then what would you use over here? Equal to, greater than, less than? I guess not equal to. Remember, this is a null hypothesis, H sub 0. Yeah, exactly. Null hypothesis, you go with equal to, and that was going to be our 57%, so 0.57. So obviously in alternative also, we would go with P. And this one, they were asking us, is the experimental course effective at the 0.025 level of significance? So what symbol would you use for the alternative hypotheses if they're saying the experimental course is effective? So when they say effective, they're saying, is it doing a better job, right? So equal to, greater than, less than, not equal to. Jeffrey, Dennis, yeah, because if it's effective, then your percentage of students who complete the course should be higher, right? So yeah, you are going with greater than. Yeah, very nice, guys. Naomi, I see your answer too. So 0.57. So all righty, so far so good. Same thing we have to verify for our test here. So again, they're having us do n times p sub 0, 1 minus p sub 0. So here Our N value is of course going to be the 18 students. So I'm just gonna carry it forward over here. So N is going to be 18. P sub 0 is the 0.57%. So when we multiply to get this here, we will do N times P sub 0 times in parentheses 1 minus P sub 0. And this is coming out to be well, not greater than 10. 4.418, and they want to do 1 decimal place. So what was that, 4.4? Yeah. So this number is less than 0. So the normal model may or may not be used to calculate our p-value. So they're not really telling us anything in terms of normal model over here. Let's get into our textbook here. I would have to say no, we cannot use the normal model since they're not really giving us. And there's our little p-value here. Trying to find where it tells us about. Okay, so this is kind of where they're talking about, using or not using the normal, normal distribution, the normal value. But in this case, I would say the normal model may not be used to approximate the p-value because we don't really have any information about this being normally distributed or not. So this is actually, they're talking about why do we think this is going to be a binomial probability, because again, remember for the binomial experiment, you have those 4 requirements. You should have a fixed number of trials. You should have each, trial being independent from each other. Your probability for each trial has to stay the same. And oh boy, I'm missing one more. Hopefully it will show up here. So there has to be a fixed number of trials. You can only have, 2 outcomes. So you can only have a success or a failure. So 2 mutually exclusive outcomes or 2 outcomes that can occur simultaneously. So definitely exclusive because you obviously don't want, success and failure happening at the same time. The trials have to be independent and the probability of success is fixed at, because this should be a likely chance, what will that be? Will this be 0.5 or 0.57? Our probability fixed at each trial. I'm actually going to try 0.57 because that's what given to us, and let's see what that comes out to be. Alrighty, very good. So you are actually basing it off of the probability that's given to you from the typical math development class. Okay, so this is where we're getting into calculating our p-value over here. So determine the p-value using the binomial probability distribution and then determine conclusion for your hypothesis test. I'm actually going to come back over here. Okay, so if my memory serves me correct, and it's been a long time since I've done this example, I believe our p-value is the same, the p hat that we calculated before, but here your p-value is going to be, that x divided by n, which in our case was 14 out of the 18 students that they are hoping will be successful. So that's going to be the 14 out of 18, which is repeating 0.7777, rounded to 3 decimal places. Oh no, okay. So this is going to be right-tailed because we do have greater than. So the probability of X or more successes, well, didn't we do that?
Isn't it 0.778?
What did I type in? Oh, I did 777. Okay, I think you might be right. Okay, they're telling us for the right-tailed test, the p-value is the probability of obtaining X or more successes. So what am I doing wrong over here? Because we've got 14 that they want to complete have completed the course with the 18 enrolled.
Don't we just assume the old p-value of 0.57?
But see, that was our initial probability. Let's take a look at an example. Yeah, see, they also did 219 out of the 500. And yeah, that's what they're giving us over here. From a random sample of 500, we had 219. Well, we've got a final check. So let's see, it should actually be 0.058. Okay, so we are definitely doing something wrong over here. But that's how I remember calculating the p-value. Okay, you know what I'm going to do, because it's already 4 o'clock and I don't want to keep you guys here longer. And like I said, I didn't really get a chance to work on this example. I will create a video of the remaining part of the problem. So we'll start by option D and I'll walk you guys through that process. And I will put that recording, when I put my lecture recording for today, I'll put it through that. So that way you can kind of come back and take a look at the second half of this. Because I honestly thought you just did 14 divided by 18, but as you can see, that's not the answer we're coming up with. So I'll go ahead and finish this problem, put the recording in, and share that with you guys on D2L, and I'll send in message out letting all of you know to go look for that recording. And then let me know. I'll be here later this evening or tomorrow if you guys want to have any questions and you want to go over it or anything like that. So yeah, I'll leave you guys here and then let me know if you have any questions, guys, and we'll pick up from there. Okay. Alrighty, so I will see you on Wednesday. Try to get as much of this homework done, and then whatever questions you have, let me know by tomorrow, and just keep a lookout for a message from me for the remaining part of this. So have a wonderful evening, guys. And if I don't see you any sooner, I will see you on Wednesday afternoon. So take care, everyone. Have a good evening. Be careful. Bye, guys.